All right, chapter 14, ideal gas law and kinetic theory. If you've had chemistry, this is a bit of a review. Bit of a review. Said a little too fast, I suppose. Um, if you haven't had chemistry, well, welcome to ideal gas law and kinetic theory. Uh, it is a fun thing. And I'm not sure why I put a picture of the La Brea tar pits on there other than bubbles of, say, methane rising to the surface. But it's pretty cool if you go there. It's just like a tar pit in the middle of Los Angeles. It's the only reason I ever wanted to go to LA. And I did. And I accomplished what I wanted. Oh, I also went to the Museum of Tolerance. That wasn't very good. I was more hopeful for that. But yeah. Molecular mass, the mole, and Avogadro's number, Na. This is Avogadro's number, if you don't recall, from your high school chemistry class, which pretty much everyone has had at this point. It's just a short way of writing it. Avogadro's number. Recall that one mass unit is 1.6605 times 10 to the negative 27th kilogram. And that 1 gram mole of a substance contains as many atoms or molecules as there are atoms in 12 grams of carbon. And Na, Avogadro's number, is going to be 6.022 times 10 to the 23rd. If I happen to write 6.02 times 10 to the 23rd, I apologize, but that's the way I learned it in high school. And despite teaching this, doesn't really change the fact that I still do the same thing I learned in high school and I don't carry it out that one extra digit. Generally won't make a difference on your homework all that much, but you do have a 2% tolerance, so there could be some situations. So it's best to carry it out to 6.0222. Sorry, 6.022. But if I do that, I'm sorry. I can't get it out of my head. I've tried. I can't. It's just ingrained. Um, the number of moles N in a sample is capital N divided by Na. And where capital N is your number of particles. And that gives you M divided by your mass per mole. And we'll come back to that here momentarily. Let's see here. One other thing. Oh, sorry. I wanted to say one more thing. I was trying to remember. Another thing that we can write here is that we could say that the mass of our particle is equal to the mass per mole divided by Na. In case we wanted the mass of our particle, it's just kind of rewriting the top thing. So, yeah. Anywho, ideal gas law. All right, ideal gas law. The pressure of a gas is proportional to both the temperature and the number of moles, and it's inversely proportional to the volume. Um, it says putting it all together, we get that P is proportional to NT 1 over V, and I'll kind of show you where that comes from here in a moment. There's a little dot right there. This is the proportionality constant. Or sorry, this just means proportionality. We'll get to that part, the proportionality constant, in a moment. But that just means proportional. That's what that symbol means. Anyhow, well, basically put, let me kind of write this over here. We know a couple things experimentally. We know that pressure is proportional to temperature, and this will occur at a fixed volume. So if we keep the volume fixed, we know that if we increase pressure inside like a sealed container, it's going to increase the pressure, the temperature. Well, how so is that? Well, we haven't got to this point yet in this chapter, but basically the speed of the molecules kind of, sort of helps determine temperature, and at a higher pressure, you're going to have more collisions, more speed, and it's just going to have a higher temperature. So that's one thing. We also know that pressure P, let me try to find my little icon here. That's proportional to N, your number of moles, and that's going to be at a fixed volume and temperature. So basically, the more particles you have, the higher pressure, which completely makes sense if you envision a gas inside of a container. Another one we've got is we know that pressure is inversely proportional to the volume, and that's at a fixed temperature. So if we hold temperature constant and we increase pressure, it's going to decrease the volume in order to accommodate for, you know, keeping that temperature constant. So knowing those three things, we can say then, by putting it all together, that P is proportional to NT over V, which is the exact same thing right up here. So there's no real proof to get this. It's just more of experimental data and what we've discovered. And so what we end up getting is our classic chemistry equation, PV equals nRT. And R is new. It is your ideal gas law constant, 8.31 joules per mole Kelvin. Has to be in Kelvin. Big thing there. Glad I just said that. Kelvin. You can't do this in Celsius. That's a big mistake a lot of people make. Everything must be done in Kelvin because the proportionality constant's in Kelvin. The proportionality constant doesn't really mean anything. It's just a constant just to make things work. Another way of expressing is PV equals nKT, and I told you this earlier, I believe in the last slide, but N is your number of particles. And to get that, we know that K is R over NA. That's just kind of a given, kind of how it's defined. And so when you make that substitution, you get PV equals nKT. So, anyhow, that's your ideal gas law in a nutshell. I don't know why I said in a nutshell because it doesn't really make much sense since I don't really deal with nuts in this class. But this ideal gas law, yes. All right, let's talk about my backpack because I like backpacks. And you should too. And if you don't like backpacks, then, well, I don't know how I feel about that. All right, so my backpack. This is my backpack right here. It's old. It's a Kelty backpack. I use it to go backpacking. There's my wife, by the way. If you're interested, she is looking at the bay. Anyways, this is in Newfoundland, northern shore, around the French northern shore of Newfoundland, around the French coast. But anyways, that's my backpack, and it actually does have a cubic volume of 5,000 cubic centimeters. So that's why I'm doing the problem, because that's what its cubic volume is. It's a big backpack, holds a lot of stuff. Held 4 days worth of provisions once. Assuming a normal atmospheric pressure of 1 atmosphere, 1.01 times 10 to the 5th pascals, and a normal mix of air. We're not going to do the 0.5% like carbon dioxide and the small amounts of argon. We're just going to say 79% nitrogen and 21% oxygen. And those are N2 and O2. So if you remember from your chemistry class, you will find these gases as molecules since they pair off together. So, anyway. All right, so we need to do a couple things here. I want to convert this cubic centimeters first because I see that and going, we're going to need to do something about that cubic centimeters. We need it to be in cubic meters, and so I know that there are 100 centimeters in a cubic meter, and so I cube everything in there. And so that ends up becoming 5 times 10 to the negative third cubic meters. So now I have it in a usable value. Why didn't I give it to you originally like that? Because that's what when I went to buy my backpack, it said 5,000 cubic centimeters. So that's why we had to convert. FYI, it was really funny, but there used to be a place called Backwoods up at Bradley Fair. And the guy there, one of the people that worked there, could do these conversions in the head from cubic centimeters to cubic feet. It was quite impressive. I can't do that in my head, but yeah. So that's why you need unit conversions. You might work it backwards. So 5 times 10 negative third, we have that. And what we need to do is we're trying to find out mass, and we know that PV, of course, equals nRT. So we're going to figure out the number of moles first. And so that means PV over RT is equal to N. And so let's go ahead and plug in what we know. Pressure, which is 1.01 times 10 to the 5th. And that's going to be, I'm going to write this newtons per square meter. And then volume, which is a 5e to the negative third cubic meters. Oh, I didn't put an equal sign. I'm sorry. We'll say equals and equals. There we go. And then RT, so this is going to be my 8.31 our joules per mole Kelvin. And then we assumed everything. Oh, I did not give you a temperature, by the way. We assumed a normal pressure, but room temperature, we assumed it's 25 degrees Celsius or 298 Kelvin. I'll try to put that in the one that I put on, like the PowerPoint or the PDF. I meant to put that on there, but I didn't. So 298 Kelvin. Sorry about that. All right, Kelvin cancels. You get meters squared down here is going to cancel with the cubic meter right here. That gives you a Newton meter. Newton meter is joule, and joule's on the bottom there, so that leaves me with nothing left more than a mole. Yay, that's what we want. All right, so math and that, you get around 0.2 moles. I think I rounded that, but it's fine. So, all right, so you get around 0.2 moles, and then I want to figure out, well, about how much of that is going to be nitrogen and about how much of that is going to be oxygen. Well, I can take my 0.79 times my 0.2 moles, and I'm going to carry that out another digit here, so 0.79 times 0.2. It's going to give me around 0.158 moles. And I lost my cursor. There it is. So 0.158 moles of N2. And then we're going to do this again. We've got 0.21 times 0.2 moles. And so 0.21 times 0.2 moles is going to give me 0.21 times 0.2 moles, and that's going to give me, oh, there it is, 0.042. And that's of O2. Okay? All right. So, knowing that, I need to figure out how many moles I'm going to have, or grams I'm going to have of each of these. So I can take my 0.158 moles that was of nitrogen. And I know that nitrogen is 14 from the periodic table, and it's 2 nitrogen, so I need to put 28 grams per mole. And then moles cancels out, and I get 4. Do that one more time. 0.158 times 28. Yeah, 4.42. I had that up already, but I wanted to double check myself. And now we've got 0.042 moles of oxygen. And I know, so I go 0.042, and I'm going to multiply that by, oh, sorry, didn't write it in here. That'll be 32 grams. Oxygen 16, it's molecular, so I need to put it as 32 grams per mole, so moles cancels. But yeah, I'm doing 0.042 times 32. I was jumping ahead. Sorry. And that's going to give me 1.344. I'll just say 1.34 to keep it the same. So, almost 6 grams of air I have to carry around my backpack. Obviously, it's not weighing me down, and it's kind of weird to think about air as having a mass, but yet it does have mass. It takes up space. So yeah, fun times. Okay, the next 2 examples come from the book because they're pretty good examples. First one of all is beer. Beer is essentially liquid bread. Bread's good for you, so beer's good for you. Good logic there. Basically put, if you ever look at beer, the little bubbles at the bottom are really small, the bubbles at the top are larger. So it appears that the bubbles actually grow larger as they go to the top, and they actually do. The question that the conceptual example asks is essentially why, or what variable is causing said bubbles to grow larger. And I think they gave just like 3 examples, the pressure and the temperature and the number of moles are the ones they looked at. Not volume. The volume's not changing, not appreciably. And then the temperature is not changing. So, because the glass of the beer we assume to be is uniform. So that brings it down to either the pressure is causing the bubbles to get bigger or the number of moles is causing the bubbles to get bigger. The bubbles will nearly double in size. So that means at the top, it would have to be 2 times the atmospheric pressure in order to double the size of the bubbles. And I could figure that out to have like a gauge pressure of an atmosphere. We could use then P is equal to rho GH, going back to a previous chapter, to figure out how high that would need to be. Well, the gauge pressure would be 1.01 E5, so 1 atmospheric pressure beyond that. That's why I call it gauge. And then the density of beer is around 1050 kilograms per cubic meter. You don't need to know that necessarily. Well, I mean, you can memorize that. I mean, it's a good fact to know, but it was given in the problem. I just don't have enough room to fit it all on a slide, basically. And then G, of course, is 9.8. And then H. And then 1.01 E5 divided by 1050 divided by 9.8. You would need to have a glass of beer be 9.8 meters tall if it were the pressure that caused the beer bubbles, or the bubbles of carbon dioxide, there's carbon dioxide in beer, to grow. So what it actually is N, the number of moles. So the number of moles actually grows. I'm really not writing this well, I'm sorry. Keep clicking this little button that causes me to do fun things, or not fun. So the number of moles is increasing as you go up. Basically, the carbon dioxide acts as like a nucleation point. Nucleation is like raindrops. Every raindrop has a nucleation particle. Generally, it's like a speck of dust or a pollutant or something like that. And they have to have something to form on, just like when you have a glass of ice water and the dew forms on the outside of it. I guess I don't really call it dew, but the condensation. I guess you could call it dew, but you get what I'm saying. And so those nucleation sites, those are the carbon dioxide bubbles, and more carbon dioxide is just built up, and so that's why it actually grows, and you see this little stratified, cool thing of your bubbles in your beer, which is liquid red, which is like it's good for you. So yeah, that's why we did this problem, and King of the Hill, because I tend to like that show. Anywho, so yeah, thought I'd do that problem, just because it was interesting enough. Boyle's law is the next thing we'll talk about. Robert Boyle found that if temperature is held constant, pressure is inversely proportional to volume. So basically, what really this boils down to is if N, your number of moles, and your temperature is constant, then PV equals nRT. Is basically P is equal to some constant over V, because everything else is constant but your pressure and volume. And so that's what leads to this equation. Sorry, I'm trying to find my cursor here. PI VI is equal to PF VF. Is that your initial pressure and your initial volume is equal to your final pressure and your final volume, as long as your number of moles, I didn't finish the word constant, as long as the number of moles and the temperature are held constant. This is an example of pressure versus volume curve. These little lines represent isotherms, iso meaning the same, therm, temperature. And this isotherm for the boiling point of nitrogen is around 77 Kelvin. And then this one is for hydrogen and helium, 4 Kelvin. And you can see that they're inversely proportional based off of the curve as well. So that's kind of why it's there. But yeah, Boyle's law is kind of interesting in that regard. And there is a huge application of Boyle's law, and that's scuba diving. If you've ever been scuba diving before, I've never been scuba diving. I don't have what you call a swimmer's body, so I'm not going to be doing some body diving. But if you have, then you might know a little bit about Boyle's Law because they kind of teach you some of that stuff. But basically put example 4, shortened version so I can kind of fit it onto one page. I gave myself another page so I have enough room to write. But basically you have a special valve. Well, let's start here. So when you go scuba diving, you the big issue is your pressure in your lungs needs to equal the pressure at that depth. And so your pressure tank is trying to keep that at the same pressure. And there's a special valve and automatically adjusts the pressure of the air coming from the scuba tank, and it ensures that your air pressure and your water pressure are at the same at all times. The tank has a volume of 0.0150 cubic meters in this example, and has an absolute pressure of 2.02 E times 10 to the 7th pascals. We assume the diver is going to consume air at 0.03 cubic meters per minute, and the temperature is constant. That's key there, so we don't have to worry about the temperature. That way we can use Boyle's Law. How long can a diver stay at a depth of around 10 meters? That's around 32.8 feet. Actually, exactly 32.8 feet. The density of seawater is going to be 1025 kilograms per cubic meter. So you got to use Boyle's Law here, and there are some liberties with this problem, but it's still pretty interesting. We know that PI VI is equal to PF VF, and it's implied that the volume of the container, at least of the breathable air, is changing. And so the values that were given, the 2.02 E7, the 150 times 10 negative second, there you go, save that one. This is going to be your VI, and this is actually your PI. So we don't know PF or VF. That's kind of the issue. So how do we get PF or VF? Well, we remember that pressure is equal to rho GH, and that would just be gauge pressure like we did in the last problem, but we need pressure beyond an atmosphere, and so we'll add that to 1.01 E5 pascals. That way we account for atmospheric pressure. And I didn't put a subscript on there because I suck, but let's stop sucking and let's put PF. There we go. And so that's how we would get that final pressure. And so that becomes PI VI equals rho GH plus 1.01 E5 pascals times VF. Okay, so that doesn't quite get us where we're going. I mean, that'll help us solve for volume, but why do we even need volume is the question. Well, where am I going with this? Well, this goes back to a previous chapter. But if we remember, remember, berries. Your change in volume over Q, your volumetric flow rate, which they gave us as 0.03 cubic meters per minute, not in seconds, but it still can be used. That's going to be equal to time. And that's from a previous chapter. So that's what I'm going to be using is that change in volume. And we know that change in volume is nothing more than VF minus VI over Q. Now we're talking. Now we can actually use this. So I'm going to write this out. Basically, if I solve this for VF, I'm going to go ahead and do that. That gives me, and I'll write it out, PI VI. Let's get myself a little line because this might be long. Okay, PI VI over, and that's going to be rho GH plus 1.01 times 10 to the 5th pascals. And so this is all my VF, by the way. So I'm going to put this in brackets to say, hey, I made a substitution. And that's all minus your VI. And then that's all over. Thank you for this. I'm so happy I have this little ruler thingamabig. And that's all over your volumetric flow rate of Q. And that will be time. And so now we can use Boyle's Law to figure out how long someone can stay at a certain depth with essentially without dying, which is a good idea because we generally don't want people to die. And at least that's generally how societies work. Okay, well, let's plug in some crap and see what happens. All right, so PI is going to be 2.02 times, I think it's 2.02. 2.02 times 10 to the 7th pascals. VI was 0.015 cubic meters. I really hope I'm not going to run out of room. And then that's over rho, which is seawater, and I put that somewhere 1025. G, which is 9.8. H of 10 meters plus 1.01 E5. So there's that, and then minus my VI, which is 0.015 cubic meters, all over and that's going to be all over 0.03 cubic meters per minute. Now, I didn't change it to seconds because the book didn't do it. I mean, I could have and changed it back. It really doesn't matter in this case. It's best to always go with the standard metric units, but in this case, I know I can get away with it. Anywho. And it gives you a time, and I went ahead and calculate that earlier because this is pretty nasty, and I want to make sure I didn't make any mistakes on it. You get around 49.6 minutes. So that's kind of the fun thing about this Boyle's Law is we can actually use it to make predictions about how long you're going to have breathable air, which is kind of important. Let's say you're on a salvaging operation, or maybe you're a diver in the Navy, and there's all sorts of things you can dive, reasons you can dive for. Once again, don't have a diver's body, don't really know that world, but I'm sure some of you may have actually done that. And every once in a while I have a student in the Navy, and they may have done some diving too. So, anywho, we will move on to the next question, or the next thing. Related to what we did earlier, Boyle's Law, you do have Charles' Law, which relates volume to temperature if the pressure and the mole number are held constant. And you get VI over TI is equal to VF over TF. And so it's similar to Boyle's Law, except this case we hold pressure and mole number constant. This is kind of just a small little addition in the chapter. It's not as big as some of the other things, so we don't spend as much time talking about this. But it is included, so I go over it. Okay. All right, kinetic theory of gases. This is probably one of the more important things, and you kind of went over this in chemistry a little bit, so it should not be a huge surprise to you. But the kinetic theory of gases basically is, at a very simple level, is how do we understand temperature in terms of what the particles are actually doing. Well, we could start by drawing a box, because drawing is the new drawing. I don't know. We got to draw a picture right in the box. All right, so I'm going to draw a picture, and let's say it's initially going, here's my little particle. It's initially going this way, and it turns around and goes that way. Okay? Just a particle in a box, right? Well, okay, so let's say we want to know force and relate that to momentum. Our force, impulse, momentum equation, F delta T is equal to M delta V. That's what we're going to use. And so the force is going to be M delta V over delta T, and then M, change in velocity. So it's initially, the final velocity was going to, it really doesn't matter whether I do left or not, but the final velocity, I think I said going to the right, so that should be mv, and then minus a negative mv, which is going to the left, over delta t. And that's going to give you 2mv over delta t. Okay, so that at least gives me something with relation to force with the particle, but doesn't quite get me really where I want to be. And I don't even know what the time is. Like, how long is that particle going to be there? Well, okay, let's come over here and write it down here. So we have F, and then we have 2mv up top. Now, I can substitute something for delta t. This box, we'll say, has a length L, and it's going in a back and forth motion. So if I say 2L over V, that will give me the time. 2L is a length, velocity is a rate. Length divided by rate is going to give me a time, and that's how long it takes to traverse that little track back and forth. And so then I could flip up my V, and that's going to give me mv squared over L. And that's, of course, equal to F. Then, okay, well, that's a little bit better. Now, this is just for one particle. There's more than one particle in a box. Box being this office that I'm in right now. There are definitely more than one particle. There's definitely more than one particle in here. So, we need to account for that. So what I can do is I can multiply this by n, the number of particles, but I will divide it by 3 because the box, after all, has 3 different dimensions: length, width, and height. So this is going to give me, and I'm going to take some liberties here in a second, n over 3, then m v squared bar, more on that here in a second, over L. Okay, what is this v squared bar? Well, there's something called root mean squared, VRMS, and that is the averages. Sorry, that is the square of all the averages, because it follows what's called a Maxwell's distribution, and you want to find the you want to use the velocity that accounts for all of the average speeds of all the particles. It's something a little bit beyond the scope of this class, at least for this semester, but that's essentially what's going on. VRMS. And I didn't even put equals there. Whoopsie. Sorry about that. Let me rewrite that again. That was bad of me. So that's VRMS is equal to, and then root of V bar squared. So, and so that's where that comes from, and that's, I put a 2, and no, that 2 is a little low, certainly low. That's a squared, by the way. I'm just struggling today with my squares, I guess. Okay, so we'll make a substitution for VRMS. So that's going to give me n over 3, and then times that by mVRMS squared. Stands for root mean squared, by the way, over L. Now, okay, I need to work a little bit with that. We know that our force from earlier, we know that pressure is force divided by area, right? And so I also know that force is equal to pressure times area. And so what I want to do is make that substitution. And that's what we're going to do next. All right, so let's do that. That gives me a PA equals n over 3 m VRMS squared. This 2 looks like it's part of that squared. Sorry, or mv squared over L. That L. There we go. I want to get that out of there so it doesn't look too bad. VRMS squared over L. So we have P and an A. Well, okay. Well, if I take A and I multiply by L, I get volume, right? So that's going to give me PV is equal to N over 3 mVRMS squared. Well, just VRMS squared in that case, because I took out my L. Okay, this is working out a little bit better. Now my next step is to put this in a more familiar form. What do I mean by that? Well, okay, let's keep holding our PV here. Let's say I do 2n over 3. and then I'm going to do mv RMS squared over 2. Then this is going to look like, still being PV by the way, this is going to be 2/3, ooh, that's a bad 3. That's going to give me 2/3 n, and then that's going to give me times 1/2 of mv RMS squared. Look familiar? Yeah, 1/2 mv RMS squared. So that's actually going to give us the average of the kinetic energies. So PV is then equal to 2/3 n Ke bar, the average of those kinetic energies. So this then relates the average of the kinetic energies of all those particles to the pressure and the volume experienced by, some gas in a box, so to speak. And so that's kind of cool. But we can kind of take that a little bit further if we want. We know that, rolling down here a little bit, because I'm running out of room. Oh, there we are. Sorry. We also know that from earlier that PV was equal to NKT. And so since we know that PV is equal to NKT, I could take that left-hand side, substitute in NKT, then in for PV. And so that's going to give me 2/3 N Ke bar. So that's kind of cool. And then notice that my n's then cancel. And then I can throw out my 3/2 to the other side. Throw over, rather. So that's going to give me my 3/2 kT. And that's equal to the average kinetic energy of the particles. So based off of the average kinetic energy of the particles, we can extract temperature based as long as we have that proportionality constant. So this is a unique way of figuring out what that temperature is. So temperature is just nothing more than how particles are just interacting and moving together. So this, I feel like there's something I'm missing here off the top of my head. I wanted to add something, but I can't remember. Well, we can still go with this, but the next slide talks about, well, we're going to utilize that to look at the internal energy of an object. Maybe that's what I was thinking of. Internal energy of a monatomic gas. So it turns out that the internal energy is purely translational. There's no real rotational motion to speak of, and so the only real energy that's coming from it is the translational, and that is the internal energy. So what we can say is we have U, which is energy, and I think I talked about how sometimes I want to write U for potential energy. There you go. And that's equal to N3 halves kT, or U is equal to N little n moles, 3 halves RT. So kind of shows you the relationship between the two. This basically means that internal energy depends on both the number of moles and the temperature for any ideal gas. So that's kind of fascinating. Something else that the book kind of talks about, which I always feel like it's common sense, but I should probably mention it, is temperature is a very relative term. It's based off of having a collection of particles, because they say it's cold in space, but it's really because there's particles, but there's so few of them that you may only have a handful hitting you at any given point in time. Or maybe you have to wait moments between getting hit by particles. And so you can't really have temperature of an individual particle. It doesn't really exist. And that's kind of why we have this quasi-weird root mean squared and all this other jazz that you've never seen before, but actually not jazz, more math. It's because at some point, the definition of what temperature is tends to break down. Just like how they say it's really hot in the ionosphere, but there's not a lot of particles there, so it's kind of weird. Nevertheless, yeah, so that's what the internal energy of our particle is. And once again, we neglect the internal energy, the rotational energy for internal energy because it's small and negligible. We maybe should do a problem on that. So this is something I got from something in Kansas. Where did I get this from? K-State? Radon levels in Kansas from the Kansas Department of Health and Environment through the Kansas State University. So if you're in a county with yellow, not a lot of radon in your basement. Orange, you got some radon in your basement. Red, lots of radon from your basement. Oh, where does this radon come from? Okay, so basically it's from the radioactive decay of materials, and then generally goes up through your cracks in your basement. And radon is big. It's very heavy. Radon has a well, let me write this out because I'm going to need this anyways. But the atomic mass of radon is going to be 222. So it's huge. And so it doesn't tend to, go up within your house. It just tends to stay in your basement. Anyways, so let's say you have 888 grams of radon and it's lurking in your basement. We want to know the average translational kinetic energy if its temperature is 20 degrees Celsius. Okay, so different ways I can maybe approach it, but I'll just do what I've got here using what we last talked about. Its kinetic energy is essentially its internal energy, as I told you. They're one and the same because we neglect the rotational energy. So I can just use the fact that U is equal to 3/2 nRT. I didn't choose the KT, I chose the nRT because I need to figure out what the number of my moles is. And so how do I do that? Well, we know that it's 222 grams per mole of radon. And we have a total of, I really wrote that backwards because we want moles. I mean, I could do it this way, but it's just going to look messy. I'm just going to rewrite it. Sorry. So we have 1 mole for every 222 grams of radon, and we have 800, and I think I made it 88. I want to make it number clean. I did. 888 grams of radon. Yeah, I could have done it the other way. I would have had to invert it at the end. I just felt like it's going to be easier this way. I made it a clean number, so let's say you have 4 moles of radon in your basement. And so now that I know that it's 4 moles of radon, I can figure out that internal energy. So U is equal to... that's going to give me 3/2 of 4 moles. R is my 8.31 joules per mole Kelvin. And my temperature is 20 degrees Celsius plus 273, because remember, they need to be Kelvin. So that gives me 293 Kelvin. And so Kelvin cancels, yay. Moles cancels, yay. They'll lose your unit of joules, which is what you wanted to begin with. You wanted an energy unit. At least I wanted an energy unit. You may not have wanted an energy unit, but I wanted it all along. That's all I could think about. All right, 1.5 times 4 times 8.31 times 293. It's going to give me a big number, 14,609 joules. And yeah, it did ask for the translational kinetic energy, but remember that is the internal energy, all things being equal. So we could use the U equation, or instead of using what I showed you earlier. But don't worry, we're going to use that. That's now. All right. Last problem. Let's say you have a cubicle box with neon inside of that box, neon gas. So like putting this little Nintendo sign inside of a gas. Only $13.99. Payment plans available. And let's say the length of the side of each box is 0.3 meters in its cubicle. So you have 1 mole of neon gas at room temperature, 293 Kelvin. We want to figure out the average rate in atoms per second at which the neon atoms collide with one side of the container. The mass of a single neon atom is 3.35 times 10 negative 26. So we need to figure out some sort of rate of atoms per second. And so I'll start with this. We have rate. We'll just call it rate, for lack of a better word. And I know I need number of atoms per second. And I know they gave me the number of moles. And I know that there are an Na, 6.0222 times 10 to the 23rd number of atoms in a mole. And so if that would give me the number of atoms divided by time. There are 3 dimensions. 3 different dimensions to account for. And so I'm going to divide that by 3 to account for all of said dimensions. Okay, well that's kind of a working model, at least. We don't know time, but I know the trick from last time. In my box, we use the fact that if we take 2L divided by the velocity, that gives us the time. Well, now we know it's actually a root mean squared velocity, so I can make that substitution down here, and I can get NA over 3 times 2L over VRMS, and then that's going to give me NA VRMS over 6L. Now we're kind of at a stopping point. We do know the length of the container, but we don't know the root mean squared velocity of our particles. But we do know one thing. We do know from the proof I did earlier that 3/2 kT is equal to the average kinetic energy. And in that case, or rather a root mean squared average kinetic energy, we know that this is going to be 1/2 of mVRMS squared. So I could solve that for VRMS, and that gives me 3 kT over m rootified is equal to VRMS. I have a really hard problem writing that S, and I apologize. All right, back over here. So that gives me rate is equal to NA, the root of 3 kT over m over 6L. And moving down just a hair. All right, let's plug in numbers. 6.022 times 10 to the 23rd atoms. And then rootified 3. K is 1.38 times 10 negative 23rd. We haven't really used that as much. And that is joules per Kelvin. And then, might be running out of room here. No. Temperature. Okay, so the temperature was 293. If I can find it here. Okay. And then that's all over the mass, which was 3.35 times 10 to the negative 26 kilograms. And that's all in here. And then divided by 6 times 0.3. Whew. All right, let's go. 3 times 1.38 times 10 negative 23rd times 293. And then I divide that by 3.35 times 10 to the negative 26. Okay. And then I rootify that. Oh, that would have been a bad thing. And then I multiply that by 6.022 times 10 to the 23rd. And now I'm going to divide that by 6 times 0.3, or rather just 1.8. And I get around, let's just round it, quite a bit. We get around, I'm almost out of room. Scary. Okay, that gives me around 2 times 10 to 26 atoms per unit of time, and that's a second. Okay. And the seconds come from something very nasty, but your Kelvin cancels out up here. I can't find my cursor. I never can find my cursor on this thing. Your Kelvin cancels in, and then your joules are joules divided by kilogram gives you, a meter squared per second squared, then divided by your meter, and yeah, it's just pretty nasty. But in any case, you get 2 times 10 to 26 atoms per second. And that is it for the chapter.